Okay, hello, analysis 1A. We are going to go over the packet called Final Assignment on Limits. The first 4 pages of it were due in last week, on Thursday and Friday, and then the final 4 pages were due over the weekend, so you're working on that now. I'll probably just make this video for the first half of it. So let's go. Here you are being asked to just do an epsilon delta proof for this limit, and it's clear that the limit as x approaches -5 of this function is -7. Okay, let's go. What does this function look like? Well, it seems like all the action is going to be happening in the 4th quadrant, so 1, 2, 3, 4, 5 at -5. What's happening? Well, apparently -7, 2, 3, 4, 5, 6, 7, so that's -7 over there, and so put a little dot. What else? Well, when x is 0, this is -4, so we have slope 3/5, and so kind of like there we go. All right, great. A couple negative numbers in there, but that shouldn't bother us at all. What do we need to prove? We need to prove that for any possible epsilon challenge which comes in the form of a tiny number, that I can get close enough to meet that challenge. So what does it mean for the limit as x approaches -5 of this function to be -7? It means that near -5 this function gets very close to -7. How close? As close as you want. And so if you demand that I be within epsilon of -7, then I can meet that challenge by finding a delta which represents how close I need to be to -5, such that within that interval of x values, all the outputs of my function land within epsilon of -7. Okay, and so what I need to prove actually is exactly that. That for all epsilon greater than 0, there exists a delta greater than 0 such that for all x, if x is between -5 minus delta and -5 plus delta, but let's exclude -5 itself from the conversation, then the function is between -7 minus epsilon and -7 plus epsilon. Okay, so keeping in mind that that's what I need to prove, and this is what you're expected to do with these problems, to make a picture, when I say add epsilon and delta to your picture, this is the kind of thing I'm talking about, writing out the thing that we're trying to prove, and now we're going to just do it. So how are we going to do it? With a discovery phase. And in the discovery phase, you work backwards to try to find the delta that will work for a given epsilon challenge. And so to find the delta that will work, I will work backwards. I'll start with the thing I'm trying to prove. So I'm going to start with my function between -7 minus epsilon and -7 plus epsilon. And now, just work backwards. So let's go. What do I know? I know that I'm between, or I'm considering my function, which is 3/5 x minus 4, and I'm starting with this function lying between the 2 red parallel lines where I need it to eventually be. Okay, so I'm going to do some algebra 1. If I add 4 to all 3 sides of this inequality, I get -3 minus epsilon is less than 3/5 x, which is less than -3 plus epsilon. And now I'm going to multiply through by 5/3, and if I do that, I get -5 minus 5/3 epsilon is less than x, which is less than, what am I multiplying? Multiplying by 5/3. So, so -5 plus 5/3 epsilon. And so the conclusion here is that I should set delta to be 5/3 epsilon. Because this line is basically telling me, yo, any x values in between -5 minus 5/3 epsilon and -5 plus 5/3 epsilon will be the kinds of x values which, when plugged back into the function, give me the thing that I want. And so the purple thing that I circled in purple is exactly the delta. So, okay, great. This is maybe kind of obvious. And all right, once you've done a couple of these, then you just get it, I guess. So now it's a matter of us doing it. Now that I've discovered the delta that works, the proof itself should be easy. What happens? Someone challenges me with an epsilon, so I take an epsilon greater than 0, and I immediately respond to that person by setting my delta to be 5/3 of whatever they just told me. And of course this makes sense. Epsilon's always positive, so multiplying a positive number by 5/3, it will still be positive. And you know, the tinier the challenge, the tinier my response is, which makes sense because, you know, the more the closer you demand that I be to -7, intuitively, the closer I have to stay to -5. Alright, now I just have to show that this delta works. How? By proving this conditional. So what I now just need to show is that for all the x values that are in between -5 minus delta and -5 plus delta, that when I plug them into the function, that they do land between -7 minus epsilon and -7 plus epsilon. And as long as I've picked the right delta, which I have, then this should be easy and smooth. Okay, so I have to prove this conditional. How? I assume the antecedent. So I assume that x is a number in between -5 minus epsilon and -5 plus epsilon, and I just take it from there. Well, I defined delta to be 5/3 epsilon, so let me just use that definition of delta, or that's what delta is for me. So now here I am, and this is kind of familiar territory because this is this line over here with the blue arrow on it, and now I just kind of do these steps over again that I did in the discovery phase, but this time, you know, in the correct logical direction, starting with the x values and showing that they land between the parallel lines. Well, do they? Yes, because I can multiply this inequality through by 3/5, giving me -3 minus epsilon is less than 3/5 x, which is less than -3 plus epsilon. Then I shall subtract 4, and that gives me -7 minus epsilon is less than 3/5 x minus 4, and well, look, I'm just done. This is my function, and so I succeeded in showing exactly what I wanted to show, which is that the function lands between the parallel lines and therefore meets the challenge. Alright, these are epsilon delta proofs, and once you do a couple, then we just kind of move on and we don't do them again, at least this semester. Okay, good. Let's just keep going. I'll leave the video running, and we'll just try to do a couple more. So number 2 was pretty easy problem, I think. Number 2 gave you a function, and the function was defined piecewise. It's a squared minus 2 if x is negative, and it's ax over tan x if x is positive. Well, question, what is A? A is some kind of constant. And so, well, look, what could A be? A could be, you know, 0, 1, 2, 3, 4, it could be anything at all, which means that, okay, this is basically just a constant function, because if A is a constant, then a squared minus 2 is just going to be a number. So what does this function look like? I'm not going to graph it, but this is a function is going to be, you know, just a horizontal line for negative values, and then something totally crazy for positive values. Notice that the function is undefined at 0. So f of 0 does not exist. And okay, good. Well, what does the problem say? The problem says pick A so that the limit exists. So if I know that the limit as x approaches 0 of this function exists, well, that must mean that the limit from the left equals the limit from the right. So the limit as x approaches a from the left of this function has to equal the limit as x approaches a from the right of this function. And okay, what is the limit as x approaches a from the left? As x approaches a from the left? Well, now I follow the left rule, right? In other words, this function is for negative. Sorry, not as x approaches a, as x approaches 0. That was confusing. I just said and wrote the wrong thing. That's what I meant to say. The limit as x approaches 0 exists, therefore the limit as x approaches 0 from the left equals the limit as x approaches 0 from the right. So, what is the limit as x approaches 0 from the left? Well, as we already discussed, for negative x values, this function is just constant, and so this is just a squared minus 2. Maybe I should write this kind of underneath. This is a squared minus 2. What is the limit as x approaches 0 from the right of this function? Well, if x is positive, then I need to follow this rule on the right. So now this problem just kind of boils down to, what is the limit as x approaches 0 from the right of ax over tan x? And this should be something that's pretty obvious. We did problems like this. We did this problem already, but okay, if you want to break it down a little bit more carefully, well, okay, first thing you could do is you could pull an a out because it's just a constant. So I get a times the limit as x approaches 0 plus of, what is x over tan x? Well, if you wanna, if you're watching this video, then I guess you wanna see this problem done. So the thing to do is to split up tan into sine over cosine, and then you can do some algebra here. And I guess if you wanted to really go all the way out, you would write this as the limit as x approaches 0 plus of cosine, because fractions means that goes up, times like 1 over the limit as x approaches 0 of x over sine x. No, sine x over x. Alright, this is maybe a little bit overkill, but of course the big thing that we know is that the limit as theta approaches 0 of sine x over x. We know that that's 1. So, sorry, those should be thetas. So, keeping in mind this fact, of course, if this ratio is 1, then so is the ratio of theta to sine theta, also 1, because it's just, 1 over 1 is just 1. So here I'm just kind of being explicit about that, right? Because I have x over sine x, not sine x over x. Don't let that confuse you. The limit as x approaches 0 of x over sine x is just 1 over the limit as x approaches 0 of sine x over x. And, okay, anyway, this we know to be 1, and so that's 1, and that's also 1. Bottom line, the limit from the left is a squared minus 2, and the limit from the right is a. And if the problem says find all the values of a for which this limit exists, well, this limit will exist if a squared minus 2 is a. And in fact, a squared minus 2 has to be a in order for this limit to exist, because if this equation that I've just written here is false, then the limit from the left won't equal the limit from the right. In other words, the solution to this problem, find all values of a for which this limit exists, is just precisely the solutions to this quadratic equation. So, okay, I just need to solve this, and I get a minus 2a plus 1. I think I did that right. So I get a squared plus a minus 2a, yeah. Right, so answer, a is 2 or negative 1, and I guess that's just all there is to say. So basically there were two possible solutions here. There was the function where it turns out a is 2. If a is 2, then this function is just 2 for negative x, and 2x over tan x when x is positive. This function has a limit at x equals 0. In fact, it's 2. And the other option is plugging in -1 for a gives me -1 when x is negative, and -x over tan x when x is positive. And this other option also has a limit as x approaches 0. The limit from the left and the right is -1, and those are the only two possible values for a. Okay, that was like way too thorough. But anyway, there it is. Let's do another one. Okay, this is maybe the hardest problem from the whole first 4 pages, I think. Here we have, this is number 3. We're taking the limit as x approaches -3 of 2 to the negative x, and we're being told that that's 8. Of course that's true, because if you plug in -3 for x, you get 2 to the negative 3, that's 2 cubed, that's 8. And the question is, find the largest possible delta given an epsilon of 0.01. In other words, we receive a challenge, and that challenge is that epsilon equals 1 over 100. And we need to respond to that challenge with some kind of delta. So the whole task of this problem is to find the correct delta response. And by saying the largest possible delta, I am ruling out silly answers which are, however, technically correct. Such as, if you just set delta to be like, 1 over a million, then surely within 1 over a million, I will meet this challenge. Because 1 over a million is just so tiny, that's just very close to -3. So I want to rule out that kind of a silly answer that doesn't involve any thinking. So that's why I said find the largest possible delta that works. All right, let's make a picture and make sure that we understand what's going on here. I want to make my picture a little bit not to scale, because I think we want to visualize what's going on. So let this be 8, and I guess, what am I doing? 4, 2, 2, 1. Okay, so 2 to the negative x. What does that look like? Well, it's a decaying exponential function. So -1, -2, -3. When I plug in -3, I get 8. When I plug in -2, I get 4. When I plug in -1, I get 2. And so we're looking at something that looks like this. Alright, so there's my exponential function. What is going on again? I am receiving a challenge. What is that challenge? Well, the challenge is how close I need to be to 8. And in general, we call this epsilon. But here, instead of giving you epsilon in general, like I did in the first problem, here I'm just giving you a particular epsilon. So that should make the problem easier, but in fact, because this function is a complicated function, it's quite hard. It's very hard to do it in general, and it's even hard to do it for a particular epsilon. I don't know why we're either. It's even hard to do it for a particular epsilon, like I'm doing now. Okay. Well, alright, if my epsilon challenge is 1 over 100, then that makes this number up here 8.01, and this number here 7.99. So this is what I mean by not to scale. I don't want it to be so hard to read that you can't see anything. Alright, what's the task here? The task is to get really close to -3. How close to -3? Well, that's what I have to figure out, right? There's some interval here around -3 that represents x values, which when plugged into this function land between the parallel lines. That's the whole kind of point of this game. Okay, well, there are a couple things that make this problem hard, but maybe what we should do right now is just find those x values now. Okay, so let's reason backwards and try to discover what x values near negative 3 will, when plugged into this function, land between these blue lines. Okay, let's go. What do I want to know? I want to know when is 2 to the negative x between 7.99 and 8.01. Okay, so for what x values is this true? Alright, well, whenever you have a sort of variable kind of up here in an exponent, we're forced to use logarithms. So that's what we're going to just do right now. We're just going to apply the log to all three sides of this inequality, and what we get is that log base 2, 7.99, is less than negative x, which is less than log base 2, 8.01. Alright, and unless, just in case you're spooked out by that a little bit, just recall some facts about the log base 2 function. Here it is. This function is, in fact, increasing. Since it's increasing, if you give me two numbers, a and b, if a is less than b, then log base 2 of a will be less than log base 2 of b. That is to say that it is valid to sort of take the logarithm of both sides of an inequality, as long as everything is positive and everything like that. Then if one number is less than another number, then their logs are going to be in that same relationship. So this is my explanation for why this is a valid move to go from here to here, and vice versa. Okay, it's just because the log function is increasing. Well, what now? Well, I'm just going to continue doing some algebra here. I don't want this negative, so I'm going to multiply through by a negative. So I get negative log base 2, 7.99 is greater than, I'm flipping the sign, x, which is greater than negative log base 2, 8.01. And I personally don't like greater than signs. They confuse me a little bit, and here there are negatives and stuff, so let me just flip it back around, and I get negative log base 2, 8.01 is less than x, which is less than negative log base 2, 7.99. And that's pretty much it. I mean, in terms of algebra, that's pretty much it. The only question now is, okay, does this all make sense? Like, what's going on? Well, what are we really doing here? Well, first of all, let's just make sure that we even understand this, because what is log base 2, 8.01? Well, log base 2 of 8 is 3. Log base 2 of 8.01 is going to be a number that's a tiny bit bigger than 3. So the negative of that is going to be a number whose magnitude is bigger than 3, but which is negative. In other words, negative 3 minus. A number which is a little bit more negative than negative 3 is. Okay, and what is this? Well, log base 2 of 7.99 is going to be a number that's a little bit less than 3. So the opposite of that is going to be a number which is pretty much negative 3, but whose magnitude is a little bit smaller than 3. So it's going to be a little bit on the positive side of negative 3. Okay, in other words, this should make complete sense to you, and you should be able to connect this algebra with the picture, convincing yourself that you've done it correctly. This number, right here, say, is, in fact, negative log base 2, 7.99. And this number here is the negative log base 2, 8.01. And so in some ways we are done, because the goal was to figure out how close to negative 3 you need to get, and the answer is, well, all the x values between here and here are going to work just fine. Okay, but this problem is really all about being able to sort of understand, the epsilon delta definition of a limit by making intelligent, giving intelligent answers to epsilon challenges with delta responses. So what is delta actually? Delta is supposed to be a number, a single positive number, which tells you how close to negative 3 you need to be. And so we need to answer, the answer to this problem is going to be one number. It's going to be some tiny number that tells me how safe is it, how far can I drift away from -3 and kind of be safe. And alright, if you just look at this function or use some common sense, you will realize that since this function is not a linear function, since it's a kind of a function which is curving, then these two distances are not going to be the same. What are these two distances? This is a certain distance, and how would I describe that distance? Well, it's how far away -3 is from negative log base 2, 7.99. In other words, it's just 3 minus log base 2, 7.99. That number there is how far, or how much more I can, it's this distance. It's just, that's what it is. It's this distance. It's how far to the right away from -3 I can drift and still meet the requirements of my challenge. But then this number is going to be a different number. It's going to be, well, the distance between -3 and negative log base 2, 8.01. So that's going to be log base 2, 8.01 minus 3. Okay, and those two numbers are not going to be the same. And the answer to our problem ultimately is going to be one of those two numbers. Because I'm forced to give an answer which is just one number, one delta. Okay, well, which is it? Now we're going to just look at our picture and just use some of our basic knowledge about exponential functions. And okay, what we see is that this function has a kind of a slope which is, getting increasingly bigger. In fact, it's an exponential function, so it's just growing and growing faster and faster. And so just position yourself right here at -3, 8, and let x get a tiny bit, let x get a little bit less than -3. You're going to break free from this top parallel line. But if you're here at -3 and you let x get a little bit bigger than -3, which is to say, closer to x equals 0, then you're also going to break through the lower parallel line. But because this function is sort of steeper to the left, you're going to exceed 8.01 faster, so to speak, than 7.99. In other words, you have less wiggle room to the left of -3 than you do to the right. That just is to say that this is the smaller of these two numbers. This is definitely the smaller of if you're comparing these two numbers, these two distances that I looked at, this one is going to be a little bit less than this one. I think that's just intuitively clear because it takes kind of less time, so to speak, moving left for the function to grow big enough that I exceeded my bound of 1 over 100. Therefore, the answer to this problem is to just set delta to be log base 2, 8.01 minus 3. That is the positive number, that's the largest positive number, which serves as an answer to this challenge. If you stay within log base 2, 8.01 minus 3 away from -3, then you'll be perfectly matched on the left, and on the right you'll have a little bit of extra room. But if you chose this one, that would be wrong because you don't have that much room on the left. So all right, I made that as clear as I possibly can. So I think that's good. All right, let's go a lot faster now because I think after that there are no more sort of like very tricky problems. They're just kind of maybe algebra tricky, but not actually so hard, perhaps. So let's go. Okay. Number 4 says, what is the limit as x goes to 0 of sine squared x times cosine 1 over x? Okay, actually it just says prove that this limit is 0, so they're already telling you what it is. You just have to show that it's true. Okay, well, why is this 0? The sort of wrong thing to do would be to split this up into the limit as x approaches 0 of sine squared, and the limit as x approaches 0 of cosine 1 over x. This would be wrong. I feel like we've done this problem already 5 times, but it's not quite exactly this one. This would be wrong because what is this limit? Well, this limit is just 0, but this limit does not exist. And it's possible for this factor to this function to go to 0 and this limit to not exist and for the product to be 0. In fact, that's what happens in this case. But it's not true in general that when you have 2 limits of this form that you can conclude that, that the answer is 0. So, so we need to do something else that's kind of more advanced, and actually the problem just says, use the squeeze theorem. So, okay, how do you use the squeeze theorem? Well, you just observe that cosine is always between -1 and 1. That's just a fact. And sine squared is always positive, so if you just multiply through by sine squared, then the very function that we're interested in is guaranteed to be between negative sine squared and sine squared. If you want to make a picture of this, therefore, there's like a sine squared envelope, you might say. And so, what does sine squared look like? Well, it's going to have, it's going to be sine or whatever. So maybe that's not the most accurate graph, but sine does look like that. Sine squared. In fact, we've done this in a previous exercise. And so, all right, then it's going to look kind of, that's negative sine squared x. So I'm not sure what's happening. I don't care what's happening kind of elsewhere, but near 0, my crazy cosine 1 over x function is being kind of squeezed between this envelope of sine squared and negative sine squared. That's the intuition, and the name for this is the squeeze theorem. So how do you apply the squeeze theorem? You first establish this inequality, which is just clear from multiplying through by sine squared, and then you show that these 2 limits are going to the same place at 0, and of course they are. What is the limit as x approaches 0 of sine squared? The answer is it's just 0, because sine of 0 is 0, so there's just nothing to talk about there. And the limit as x approaches 0 of negative sine squared is also 0. And so these sort of 3 facts together, that the function I care about is between these 2, and these 2 are both doing the same thing. My conclusion is, by the squeeze theorem, the limit as x approaches 0 of sine squared x cosine 1 over x equals 0 also. That's all you have to do. That's kind of what we meant by do a proof. Okay, 5. This is something that just requires some kind of algebraic sophistication, maybe. 1 minus cube root x over 1 minus x. Well, alright, if you try to directly plug in 0, of course that doesn't work. You get a 0 over 0 situation. And so when we encountered problems that were like this, for example, as I was telling some students, if this were the problem, then I think I would know what to do. And that would be to multiply by the conjugate. Because multiplying by the conjugate is kind of like the way to unlock what's really happening and to find the gap between 1 and square root x, near 1. But here, that's not going to work, right? Because the built into the algebra behind multiplying by the conjugate is that you get rid of the square root by sort of using the formula for the difference of squares. But here, this is just not a square root, it's a cube root, and so the difference of squares formula is irrelevant to me. So if you thought, I'll just multiply by 1 plus cube root x or something like that, well that's just kind of wrong. That's not going to go anywhere. If you multiply that out, you don't achieve any kind of clarity. In fact, what we need is to sort of multiply by the thing that will turn this into the difference of cubes. Actually, that's one way you could do this problem. But even a slightly simpler way to do this problem is to use the other idea, when faced with 1 minus root x over 1 minus x, the kind of sophisticated thing to do is to factor this 1 minus x into 1 minus root x and 1 plus root x. In other words, just go straight for the difference of squares, and then it just cancels and you're good. So okay, I'm going to do a similar thing here, and I'm going to rewrite this as the limit as x approaches 1 plus of 1 minus cube root x, and just on the bottom here, I'm just going to factor 1 minus x as the difference of cubes. This is the kind of thing that when you see it, then you just get it, and then it's just great. So this is 1 minus cube root x times 1 plus cube root x plus x to the 2/3. So that just is the formula for the difference of cubes, and you can just always just double check by multiplying through. You get 1 plus cube root x, but then minus cube root x, and then plus x to the 2/3, but then minus x to the 2/3, and then minus x. So that's just done correctly. And then these cancel, and then this limit is now no longer indeterminate. It's just the limit as x approaches 1 plus of 1 over 1 plus cube root x plus x to the 2/3. And now when you plug in 1, you're just going to get 1/3. So that's that. Okay, back in 1 second. Okay, we are back. Number 6 is a pretty challenging limit that says, what's the limit as x approaches 0 of sine pi over 6 plus x minus 1/2 over x? Alright, how are we going to do this? Well, if you try to plug in 0, then you get sine of pi over 6 is 1/2, so you get 0 on the top and 0 on the bottom. So this is a 0 over 0 situation, which means we need to kind of get back to work and figure out what this is. How can we figure this out? It's very unclear how we're really going to do this. We need to somehow find out what is the precise relationship between sine pi over 6 plus x and 1/2, sort of how far apart are they or something like that. And okay, in the past we've done things like multiply by the conjugate or something like that, but this is now a new thing that hasn't come up before, I guess, and you just need to figure it out. Well, there's really only one possible thing that we can do to learn more about sine pi over 6 plus x, and that is to apply the formula for the sine of a sum. So, alright, I really do expect that you just know these things, that sine of a plus b is sine a cosine b plus cosine a sine b. So it's one of the most important things that you learn in pre-calc b. And yeah, we just need this now, right? So what are we going to do? We're going to split this up into the limit as x approaches 0 of, well, what is this? I guess we get sine pi over 6 cosine x plus cosine pi over 6 sine x minus 1/2. Alright, and we've temporarily made this maybe more complicated or something, but okay, we continue. What is sine of pi over 6? Of course it's just a half, and this is, so I get 1/2 cosine x plus cosine pi over 6 is root 3 over 2 sine x minus a half all over x. Alright, and now I need to be very observant. And okay, something is just jumping out at me. What's jumping out at me is this sine x over x. And you have to just know what you're doing so well enough that you notice that sine x over x is 1. And since sine x over x is 1, it suggests that I should split up this fraction into 2 pieces. And so that's exactly what I'm going to do now. This is really, maybe I'll just do sort of all the things at once or something. Yeah, that's what I'll do. What am I going to do? I'm going to split this fraction up into 3 pieces. And I'm going to split the limit up. I'm going to split the fraction up into 2 pieces, and I'm going to split the limit up. So this becomes, maybe I'll do it in 2 steps. So this becomes the limit as x approaches 0 of root 3 over 2 sine x over x plus the limit as x approaches 0 of 1/2 cosine x minus a half over x. Okay, I guess that's not so hard to see. What did I do? Once again, I just split this fraction up into 2 pieces, kind of extracting the middle term. But I also applied, limit of the sum is the sum of the limits. Is that legitimate? Well, it's legitimate as long as the limits both exist, and I think they just do now, right? Because what is this? Well, this is just root 3 over 2 times the limit as x approaches 0 of sine x over x. And it's this thing that we knew was going to just go to 1. That's why I chose to split it up this way in the first place. Okay, now what do we get? We get plus, well, I can factor a 1/2 out of that numerator, and in fact I can just take it right out of the, I can factor a 1/2 out of both terms in the numerator, and I can just take it right out of the limit. And so we get 1/2 times the limit as x approaches 0 of cosine x minus 1 over x. And here, if you just have this memorized, then the problem is over. And in fact, it turns out that this limit is just 0. If you know that, then you're done. If you don't know that this is 0, then you have some work to do. And the work to do here, I suppose, is to, well, first of all, it's a 0 over 0 situation, so the answer is not obvious. Okay, I can multiply by the conjugate cosine x plus 1, so I get, and we've done this now sort of many times. So what is happening to this? Let's see, how should I do this? Maybe I'll just kind of put a red box around this limit, and just let's work on it a little bit more. Well, cosine squared x minus 1 is negative sine squared x. And if so this is negative sine squared x, then in fact what we get is the limit as h approaches 0 of negative sine x over x times the limit as x goes to 0 of sine x over cosine x plus 1. What did I do here? Multiple things at once. I multiply these through to get the difference of squares. Cosine squared x minus 1, I applied a trig identity that cosine squared x minus 1 is negative sine squared x. And then I split that up into 2 fractions, and I applied the limit of the product to the product of the limits. And so this gives me this. Well, now I think I'm done, because this limit goes to negative 1. We know that sine x over x is 1. But this limit goes to 0, because this is 0 over 2. And since that goes to 0, then this whole thing in the red box is 0. Then this whole thing in the red box is 0. And we end up with this kind of, root 3 over 2 times 1 plus 1/2 times 0 thing. And the final answer to this problem is root 3 over 2. So, all right, what's the takeaway here? You had to expand this out using the sign of the sum. You had to recognize that sine x over x was 1. You had to kind of split this up carefully. And it really, really helped if you had just memorized this, or I'll just say recognized that this limit is also 0. But if not, then you just had to show that it was. Okay, moving on. Number 7, determine constants b and c so that this function is continuous everywhere. Okay, this is a kind of like a, do you understand continuity question. What is this? It's some kind of piecewise function. It's a piecewise function that's been presented to us a little bit awkwardly, I'll be honest. It's a linear function in between 1 and 3, but it's a quadratic function for absolute value x minus 2 greater than or equal to 1. That's quite annoying. When is the absolute value of x minus 2 greater than or equal to 1? Let's just kind of settle that off to the side. When is the size of something bigger than 1? If it's bigger than 1 or less than negative 1. And so the way I would teach an Algebra 1 student to solve this is that this is true when x minus 2 is greater than or equal to 1, or when x minus 2 is less than or equal to negative 1. So that's an or situation. Therefore, this is going to be true when x is greater than or equal to 3, or when x is less than or equal to 1. In other words, this problem is kind of making you jump through hoops. Maybe you recognize this immediately, but if you didn't, then this was a compact way of saying something which could have been said less efficiently, but maybe more clearly, which is like, yo, follow the parabola rule for x's which are less than or equal to 1. Follow this x plus 1 rule for x's between 1 and 3 exclusive, and then go back to following this parabola rule for x's which are greater than or equal to 3. So this is just the original formulation was just a more concise way of saying that. Okay, having established that, now I realize, like, look, all three of these pieces are polynomials. All polynomials are continuous everywhere. Therefore, there's only one thing to worry about, and that is we need to worry about the places where the functions take over from each other. So I need to make sure that at x equals 1, this parabola is matching up with this linear function, and at x equals 3, I need to make sure that this parabola is matching up with this linear function. So it's really kind of just that simple. So just take at x equals 1. What's true at x equals 1? Well, the limit as x approaches 1 from the left of this function is going to follow the rule for the parabola. Well, when x is 1, I end up with 1 plus b plus c. 1 plus b plus c. But what is the limit as x approaches 1 from the right of this function? Well, if I'm a little bit more than 1, then I need to be following the linear function, and then the answer is going to be 2. Alright, so one of the things that must be true, let me make sure I have enough space here, one of the things that must be true is that 2 equals 1 plus b plus c. If that holds, then at x equals 1, the parabola meets the line. Okay, what about at 3? What's the limit as x approaches 3 from the left of this function? Well, if x is approaching 3 from the left, I'm supposed to follow the linear rule, and therefore the limit is 4. But if I approach 3 from the right, then I should follow the parabola rule, and I get, let's see, 9 plus 3b plus c. 9 plus 3b plus c. And so it better be true that 4 equals 9 plus 3b plus c. In other words, in order for this function to be continuous everywhere, the pieces must meet, and that's equivalent to saying that these two linear equations must be true. Alright, well now I'm kind of getting somewhere. What do I know? I know that 3b plus c has to be negative 5, and I know that b plus c has to be 1. So boom, subtract these two, 2b has to be negative 6, b has to therefore be negative 3, and if b is negative 3, then c has to be 4. So I think the answer is b is negative 3 and c is 4. I can just double check that. Boom, and boom. Cool. So, what does that tell me? That tells me that the true answer to this problem is the one in which I follow the parabola. Well, what's the parabola? X squared minus 3x plus 4, x plus 1, x squared minus 3x plus 4. And actually, just to double check this, we can graph this function and we can make sure that it works. And I guess that's just what I'm gonna do right now. If I have the space, yeah, I think I have the space. Let's see, Jean and bum 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 bum. So, what did I say? If I plug in 1, I get 2. So 1, 2, boom. And when I plug in 3, I get 4. So 3, 4. So there's the line. And then, what is this function, x squared minus 3x plus 4? Well, I guess it's just x minus 4. No, that just doesn't factor. Sorry, negative 1? Does that work? Yeah, what am I doing? X. No, it doesn't. It doesn't factor. It doesn't factor. Yeah, sorry. So there are not two numbers that multiply before they add to 3. Okay, so that's kind of annoying. Well, anyway, what does this function look like? This parabola. I guess I need to like complete the square or something, but I'm losing now interest in doing this properly. But this would be x minus like 3/2 or something like that, plus 9/4, but that's 16/4, so that's plus 7/4. Alright, so it's going to be some kind of parabola whose vertex is like around here or whatever. No, whose vertex is at 1.5. So 1.5 comma 7/4. So actually this is starting to make some sort of sense. And so if I were to graph this parabola, I would see that it goes kind of like this and kind of like that. Yeah, there we go. And now I will erase the part between 1 and 3 where I'm not supposed to follow this parabola. So okay, if that whole thing made sense to you, I think that was kind of worth it. In the end, I have this blue parabola that I follow until I get to 1, then I stop following it and I follow this line from 1 to 3, and then I continue on. So only this parabola, x squared minus 3x plus 4, will do the job of matching this linear function perfectly, so that this piecewise function will be continuous everywhere. Okay, back for the last couple problems in a minute. Okay, here we go. Back for a couple more limits. Here now we just have to do it. Well, I kind of almost did this exact problem already, right? I'm taking the limit as x approaches 1 of the arc sine of some stuff. What can I say about that stuff? Well, if I try to plug in 1 exactly, I get a 0/0 situation. So I need to analyze what's inside there. But we pretty much already covered this exact problem. And, well, how should we do this? The answer is to multiply by the conjugate, or even better, to just rewrite 1 minus x as 1 minus root x times 1 plus root x. And in other words, factor that denominator as the difference of squares. Why? Because if I do that, then these will cancel. And so actually this whole thing just turns into the limit as x approaches 1 of the arc sine of 1 over 1 plus root x. And if I plug in 1 now, I get arc sine 1/2, and arc sine 1/2 is pi/6. So the answer to this problem is just pi/6. Okay, what about 9? This is just only sort of slightly tricky. Taking the limit as x approaches negative pi/2 minus of secant. Okay, well I happen to know that secant is like undefined at negative pi/2. So I definitely need to be really careful. So, I mean, no one really would do this, but what we're really doing right now is we're kind of like splitting up this limit into the limit as x approaches negative pi/2 minus of secant, and the limit as x approaches negative pi/2 minus of like 1 over x. Okay, and well, in both cases, what do we get? Well, we can make a kind of a graph of secant now, I guess. What does secant look like? Here's pi/2, here's negative pi/2. We have asymptotes here and here, and so the function is going to look like this, cha-cha, and then like that. And so, alright, by consultation with this graph, we see that if x is a little bit less than negative pi/2, the secant will be negative infinity. And okay, once again, it's possible to answer this not with a graph, but with a unit circle analysis. What does it mean to be a little bit less than negative pi/2? It means you started at 0 and you went backwards pi/2, and then you even went a little bit beyond that. So we're talking about a point like right around there, whose coordinates are going to be something like 0 minus comma negative 1. And since secant is 1 over the x coordinate, then that's going to be 1 over 0 minus. So that's an alternative way of convincing yourself that secant is going to negative infinity. What about this over here? Is this just totally irrelevant? Well, it's not totally irrelevant because look, my number, my x value is negative pi over 2. So what is this near negative pi over 2? Well, it is in fact 1 over negative pi over 2. In other words, it's the number negative 2 over pi. And so it's not really relevant what this number is, since this is going to negative infinity, but it is relevant that this number is negative. And one of the cases that we discussed when we went over that worksheet called limit of the product of two functions was what happens when you split a limit up into two limits. One of them goes to negative infinity and the other one goes to a negative number. And the answer is that it's going to infinity. So this was kind of like a test of that concept. Okay, number 10. The limit as x approaches 2 of root 6 minus x minus 2 over root 3 minus x minus 1. Alright, this is just a kind of algebraically difficult, obnoxiously hard problem. We've done problems like this before, but not exactly like this. Of course, if you plug in 2, then you get a 0 on the top and 0 on the bottom. And if you've been really following kind of everything that we've been doing with multiplying by the conjugate, you will sort of recognize that I need to multiply by the conjugate here. But what makes this problem hard is, well, do I multiply by the conjugate of the numerator or do I multiply by the conjugate of the denominator? And the answer is you have to do both, right? You need to multiply by root 6 minus x plus 2 over root 6 minus x plus 2, because only by doing that will I sort of reveal the gap between root 6 minus x and 2. I need to know how tiny of a tiny number is that. Well, the only way I'm going to find out how tiny of a tiny number is that is to calculate how tiny is the difference between the squares of those two numbers. That's what's really sort of happening when I choose to multiply by the conjugate. And okay, but I also need to know how tiny the difference is between root 3 minus x and 1. Well, the only way I'm going to be able to do that is to find out how tiny the difference is between the square of that and the square of that. In other words, I need to multiply by root 3 minus x plus 1 over root 3 minus x plus 1. Alright, once you sort of think to do that, once you're sort of bold enough to try that, then I think the rest of the problem is just okay. You just have to kind of keep track of what's going on. What is going on? Well, on the top now I get multiplying these through 2, multiplying these through gives me 6 minus x minus 4, but then I leave this one, you know, don't multiply it out. And then on the bottom, I'm going to multiply these two. And when I multiply these two, I get, you know, 3 minus x minus 1 times root 6 minus x plus 2. Okay, but these both turn out to be 4 minus x. And so these both cancel. I guess I should have another set of parentheses in here. Yeah, maybe I'll just do it like that. 6 minus x minus 1. Okay, yeah, those are both just 2 minus x, and so these cancel, and therefore this limit is no longer indeterminate. It's just the limit as x approaches 2 of root 3 minus x plus 1 over root 6 minus x plus 2. And now the answer is, let's see, whatever it is, I plug in 2, I'm going to get 1 plus 1 on the top, and on the bottom I'm going to get root 4, so that's 2 plus 2, so this is 2/4, so the answer to this problem is 1/2. Okay, good. One more problem to go. Let's just do it right now. It's a proof, and the proof is one of these. It's not quite an epsilon delta proof because it's the limit as x approaches infinity. It's actually something that we did basically last semester, so this shouldn't strike you as particularly hard. I said prove that the limit as x approaches infinity of 1 over x, prove that this is 0. Okay, alright, this problem's almost like, I don't know, too easy or something. This is basically just a test. If you understand the definition, what is 1 over x function? Looks like this. And I think that the limit is 0. Well, if I think that the limit is 0, then what I mean is for very large values of x, this function gets really, really close to 0. How close to 0? As close as you want. And so I will receive a challenge. That challenge comes in the form of epsilon. And the epsilon challenge says, I dare you to get within epsilon of 0. And how do I meet that challenge? The answer is I go out far enough such that beyond that point, all the outputs of the function are within epsilon of 0. In other words, what I really need to prove is that for any possible epsilon challenge, that there exists a big N such that for all x, if I go out past big N, then the function 1 over x will be between negative epsilon and epsilon. Okay, and that's it. This is what I need to prove. So most of the task here is just recognizing that is even what needs to be done. Then actually doing it, I think, is I don't want to say easy, but it's pretty easy. How am I going to do it? I'm going to do a discovery phase. And in the discovery phase, I need to figure out how to respond to a particular epsilon challenge. Given some epsilon challenge, I have to answer with an n. The tinier the epsilon you give me, then that determines how far out I need to go. And here you could almost just guess it by playing around, because the function is so simple. It's just the 1 over x function. We did stuff like this last semester. Well, we might as well just do the algebra. We need to work backwards. We need to make sure that this is true. And here you have to have the kind of confidence, I guess, to recognize that my function's just always positive when x is going to infinity. So for positive x values, my function's always positive. So the fact that my function is bigger than negative epsilon is just irrelevant. So let me just blow that off for a minute. In discovery phase, you get to just do whatever you want. You don't need to justify your steps. The thing that's sort of important is that this function 1 over x be less than epsilon. Well, if 1 over x must be less than epsilon, and I know x is positive, then I can just reciprocate both sides, and that tells me that x is greater than 1 over epsilon. And now, I'm just done, because I have realized what to do. I should just set my n to be 1 over epsilon. Because if x is bigger than 1 over epsilon, then the thing will be true. Okay, and so now comes the actual proof. In the actual proof, someone challenges me with an epsilon greater than 0. How do I respond? Answer, I just spit back at them the 1 over the tiny number they just give me. If you give me an epsilon of 1/10, then I go out to n equals 10. If you give me an epsilon of 1 over 100, I go out to n equals 100. And now all I need to do is to show that this n works. How do I show that this n works? Well, I need to show that if x is bigger than that big N, then indeed my function stays between epsilon and epsilon. Between negative epsilon and epsilon. Alright, how do I prove this conditional? I assume the antecedent. So let's assume that x is greater than big N. Well, big N I've set to be 1 over the challenge number. And, okay, epsilon is positive, so therefore 1 over epsilon is positive. This is positive. X is bigger than this positive number, so x is also positive. So both of these are positive. Therefore, it's completely legitimate to reciprocate both sides. And if I reciprocate both sides, I flip the sign, so that becomes 1 over x is less than epsilon. And look, if x is positive, 1 over x is positive also. So now you just have to be like, dude, it's just a math fact that 1 over x is greater than negative epsilon. Why? Because every positive number is bigger than every negative number. And therefore, this is the way to do this problem by avoiding absolute values. Therefore, by putting these two lines together, I've shown that my claim has been made here, and so the problem's done. Okay, goodbye.